Morning. Today we discuss what is a tunnel diode. I, Dr. Vanna Ranga, will like to discuss this with you. The tunnel diode is associated with quantum tunneling phenomena. The tunneling time across a device is very short, permitting its use well into the milliammeter wave region. Because of its mature technology, the tunnel diode is used in special low power microwave applications such as local oscillators and frequency locking circuits. A tunnel diode consists of a simple p-n junction in which both the p and n sides are degenerate, that is very heavily doped with impurities. The figure shows it shows the typical static current voltage characteristics of a tunnel diode under four different bias conditions. The IV characteristic is the result of two current components, the tunneling current and the thermal current. When there is no voltage applied to the diode, it is in thermal equilibrium, that is V is equal to 0. Because of the high dopings, the depletion region is very narrow and the tunneling distance D is quite small, that is 5 to 10 nanometers. The dopings also cause the Fermi levels to be located within the allowed bands. The amount of degeneracy QVP and QVN shown at the far left is typically 50 to 200 milli electron volt. When a forward bias is applied, there exists a band of states that is occupied on the n side and a corresponding band of energy states that is available and unoccupied on the p side. The electrons can tunnel from n side to p side when the applied bias equals approximately Vp plus Vn divided by 3. The tunneling current reaches its peak value Ip and the corresponding voltage is called the peak voltage Vp. When the forward voltage is further increased, there are fewer available unoccupied states on the P side, Vp and Vv. In between lies V, that is the biasing voltage, where Vv is the valley voltage and the current decreased. Eventually the band is uncrossed and at this point the tunneling current can no longer flow. With still further increase of voltage, the normal thermal voltage will flow, the normal thermal current will flow, that is for V greater than Vv. From this discussion, we expect that in the forward direction, the tunneling current increases from 0 to a peak current Ip as the voltage increases. With further increase in voltage, the current then decreases to 0 when V is equal to Vn plus Vp, where V is the applied forward voltage. The decreasing portion after the peak current in figure is the negative differential resistance region. The values of the peak current Ip and the valley current IV determine the magnitude of the negative resistance. For this reason, the ratio Ip by IV is used as a figure of merit for tunnel diode. An empirical form of IV characteristics is given by I is equal to Ip V divided by Vp exponential of 1 minus V divided by Vp bracket close plus I0 exponential QV by Kt, where the first term in the channel current, the first term in the tunnel current and Ip and Vp are the peak current and peak voltage respectively, as we have shown in the diagram. The second term is the normal thermal current. The negative differential resistance can be determined from the first term of the above equation, and the value R is equal to di by dv to the power of minus 1. This is equal to minus in brackets another bracket V divided by Vp minus 1 bracket close Ip divided by Vp exponential of in brackets 1 minus V divided by Vp bracket close another bracket close to the power of minus 1. This figure shows a comparison of the typical current voltage characteristics of germanium, gallium antimonide and gallium arsenide diodes at room temperature. The current ratios of Ip by IV are 8:1 for germanium and 12:1 for gallium antimonide and gallium arsenide. Because of its smaller effective mass, that is 0.042 m0 and small band gap 0.72 electron volt, the gallium antimonide tunnel diode has the largest negative resistance of 3 devices. So this shows a typical current voltage characteristics for germanium, gallium antimonide and gallium arsenide tunnel diodes at room temperature. So here we had discussed about what is the basics of tunnel diodes. We will now try to discuss what are microwave diodes, the quantum effect and hot electron devices, the basics of them. Many semiconductor devices which have been discussed in previous chapters can be operated in the microwave region, that is 0.1 to 300 gigahertz. However, two-terminal devices generate the highest power levels per device area in system applications, especially at higher frequencies. Additionally, pulsed operation of these devices overcomes thermal limits and increases peak radio frequency power levels by more than an order of magnitude. In this chapter, we introduce some basic microwave technology and consider some special two-terminal microwave devices, including the tunnel diode, the impact diode, and the transferred electron diode device, and the resonant tunneling diode. In the past 2 decades, we have witnessed considerable research and effort in the development of device structures that could exploit quantum effect and hot electron phenomena to enhance circuit performances. Speed is often cited as a primary benefit that quantum effect devices QEDs and hot electron devices HEDs can offer. The tunneling process on which most QEDs rely is an intrinsically fast process. In HEDs, the carriers under ballistic transport can move at velocities considerably in excess of their equilibrium peak velocity. However, a more significantly advantage of QED and HEDs in their higher functionality. These devices can perform relatively complex circuit functions with greatly reduced device count, replacing large number of transistors or passive circuit components. The basic device structures and operating principles of QEDs and HEDs are discussed later on. Specifically, advantage of millimeter wave devices over those operated at low frequencies, the quantum tunneling phenomena and its related devices, the tunnel diode, resonant tunneling diode RTD, and unipolar resonant tunneling transistor, the impact diode, the most powerful semiconductor source of milliammeter wave power, the transferred electron device and its transit time domain mode, the real space transfer transistor and its advantages as functional device. So these are all the things which we will be discussing in this chapter. Now we discuss what is the basic microwave technology. The microwave frequencies cover a range from about 0.1 gigahertz, that is about 10 to the power 8 hertz, to 3000 gigahertz, with corresponding wavelengths from 300 centimeter to 0.01 centimeter. For frequencies from 30 to 300 gigahertz, we have the millimeter wave band because the wavelength is between 10 to 1 millimeter. For even higher frequencies, we have sub-millimeter wave band. The microwave frequency range is usually grouped into different bands. The bands and the corresponding frequency ranges, as designated by the Institute of Electrical and Electronics Engineers, that is IEEE. It is recommended that both the band and the corresponding frequency range be used when referring to microwave devices. The development of microwave technology was driven by the demands of shortwave length radio and later radar systems. The history of microwave started with the first experiments of Heinrich Hertz around 1887. Hertz used a spark transmitter and produced signals in a very broad frequency band and selected from these a frequency around 420 megahertz with an antenna that measured half a wavelength for his experiments. The rapid development of wireless communication products has led to an explosion in the microwave technology. Since the introduction of cellular telephone service in 1980s, there has been a rapid growth of those systems as well as mobile paging devices and a variety of wireless data communication services under the broad heading of personal communication services. In addition to these terrestrial communication systems, the field of satellite-based video, telephone and data communication systems has also grown rapidly. These systems use the microwave frequencies from several hundred megahertz to well over 60 gigahertz, the millimeter wave region. Millimeter wave technology offers many advantages for communications and radar systems such as radio astronomy, clear air turbulence detection, nuclear spectroscopy, air traffic control, beacons and weather radar. The advantages of millimeter waves over lower microwave and infrared systems include lightweight, small size, broad bandwidths, several gigahertz operation in adverse weather conditions and narrow beam widths with high resolution. The principal frequencies of interest in the millimeter wave band are centered around 35, 40, 94, 140 and 220 gigahertz. The reason for choosing these specific frequencies is mainly the atmospheric absorption of horizontally propagated millimeter waves, as we have shown over here in this diagram. The atmospheric windows where absorption is at a local minimum are found around 35, 94, 140 and 220 GHz. The absorption peak due to oxygen at 60 GHz can be used for secure communication systems. Ordinary electronic components behave differently at microwave frequencies than they do at lower frequencies. The distributed effects must be taken into account at microwave frequencies because at these frequencies the wavelength approximates the physical size of the components. At microwave frequencies, a thin film resistor, for example, looks like a complex RLC network with distributed L and C values and for different R values. These distributed components have immense significance at microwave frequencies, even though they can be ignored at lower frequencies. At microwave frequencies, capacitors and inductors are often realized by transmission line segments. Transmission lines are often used for microwave circuit interconnections as well. Transmission lines are actually complex networks containing the equivalent of all the three basic electrical components: resistor, capacitor, and inductor. Planar transmission lines are the mainstay of modern microwave circuit technology. Such lines consist of one or more flat conductors on a thin dielectric substrate with a ground surface. The figure shows several basic types of planar transmission lines: microstrip, coplanar waveguide CPW, stripline, and suspended substrate stripline SSSL. Microstrip is the most common type of transmission line. The coplanar waveguide is somewhat lossier, and that is, loss in signal propagation is larger, but it minimizes the parasitic inductance of ground connections. The characteristic impedance Z0 of the transmission line is given by Z0 is equal to under root of R plus J omega L divided by G plus J omega C ohms, where R is the resistance per unit length in ohms, G is the conductance per unit length in Siemens, and L is the inductance per unit length in Henrys, C is the capacitance per unit in farads, and omega is the angular frequency in radians per second. In microwave circuits, the resistances are typically low compared to the reactances and can be simplified to Z0 is equal to under root L by C. The characteristic impedance for a specific type of transmission line is a function of the conductor geometry, size, spacing, and the dielectric constant of the insulating material used between the conductors. So, at low microwave frequencies, resonant circuits can be made using inductive and capacitive elements. For millimeter wave and high frequency, however, the values of LC components at resonance are too small for practical implementation. Other methods for providing resonant circuits must be used. One popular section is the resonant cavity, called the tuned cavity. The resonant cavity is a metal walled chamber made of low resistivity materials enclosing a good dielectric, for example vacuum, dry air, and dry nitrogen. It is analogous to a section of waveguide with both ends shorted and has a means of injecting energy into or extracting energy from the cavity. The cavity supports both TE, transverse electric, and transverse magnetic modes of propagation. The electromagnetic wave is confined by the wall of the cavity. Energy stored in the electric field represents the capacitance, whereas the energy stored in the magnetic field represents the inductance. Both elements of the LC tuned resonant tank circuit are presented in the cavity. The resonant mode occur in the cavity at those frequencies for which the length D along the z-axis is a half wavelength. The alphanumeric system for designating modes in a cavity is T, X, M, and P, where X is E for electric dominant modes and M for magnetic dominant modes. M is the number of half wavelengths, and A is the dimension, N is the number of half wavelengths in the B dimension, and P is the number of half wavelengths in the D dimension. The general modes dependent equation for resonant frequency cavity is Fr is equal to 1 by 2 over here, 1 by 2 under root of mu E under root of m by A whole square plus n by B whole square plus P by D whole square, where mu and E are permeability and permittivity of material in the cavity. For vacuum, mu is equal to mu 0 and epsilon equal to epsilon 0, and mu 0 epsilon 0 equal to c to the power of minus 1, where c is the speed of light in vacuum. We can rewrite this equation as Fr is equal to c by 2 under root of m by A whole square plus n by B whole square plus P by D whole square. So this is all we have about the microwave devices. Thank you.